It's almost invisible. A green leaf on a supermarket shelf, slightly crisp, slightly cold, packed in silence. But behind that single lettuce head, there is a massive, intricate system in motion. A system that moves 4.1 million tons of this vegetable across the planet every year, without letting it rot, collapse, or dissolve. Because lettuce isn't just a crop, it's a fragile biome of water, with cells so delicate they can rupture with the same ease as soap bubbles under pressure. The challenge? Keeping that internal world intact, from the moment it's harvested until it lands on your plate, days later, often continents away. At first glance, cooling seems simple, but lettuce reveals a paradox that turns this cold chain into a scientific and engineering puzzle. Composed of 95% water and built from layers of extremely thin tissue, each leaf is vulnerable to something most systems ignore: latent heat. When cooling begins, energy is released inside the plant, and that energy, if not managed precisely, causes microfractures between cells. These fractures don't appear immediately. They surface as brown spots, soggy cores, and enzymatic decay hours or days after arrival. It's a delayed failure, born from an invisible thermal shock. To understand this vulnerability, think of precision sprayers used in smart agriculture. When applying pesticides, modern sprayers adjust droplet size based on viscosity, airflow, and boom angle. Even a slight change in wind speed alters the spray pattern. Lettuce requires the same sensitivity, not to spray, but to air. When cooled in stacked cartons, airflow must be distributed like a calibrated mist, gliding over and between every layer. If one carton receives too much velocity, the outer leaves desiccate. Too little, and the center warms just enough to invite decay. This is not just theory. It's physics applied to biology. And the deeper engineers looked into this problem, the more surprising the analogies became. Naval refrigeration systems, for example, face a comparable dilemma. In polar exploration vessels, even minor internal frost buildup along the hull can weaken structural integrity by forming crystalline layers that slowly expand and rupture the metal under pressure. Lettuce cells, exposed to sub-zero airflow without regulation, suffer the same microscopic damage. Invisible ice crystals form inside the tissues, slowly undermining their structure from within. Yet despite these complex dynamics, most cold chain systems rely on a misleading metric: the ambient temperature of the container. A stable readout means nothing if the core of the vegetable is out of sync with the surrounding air. What matters more is the dew point differential, the moment when moisture condenses within the produce, starting the countdown to spoilage. That dew point, which varies from field to field, batch to batch, is often ignored, but it tells us far more about future rot than any number on a control panel. And here's the final irony. While high-tech ships use pressure and fluid dynamics to control internal temperatures under extreme conditions, most global lettuce shipments still rely on average air temperatures pumped into a sealed box. No sensors in the stems. No modeling per crate. No mapping of internal airflow layers. Just tonnage, refrigeration, and time. It raises a question that should no longer be rhetorical. If we can manage the hull integrity of a ship crossing the Arctic with internal fluid inertia and pressure control, why do we still cool lettuce like it's steel instead of what it is? A living structure in thermal motion. That's the paradox, and it's just the beginning. Refrigerated containers are designed to deceive the eye. Their outer surfaces gleam with thermodynamic control. Their sensors report stability to the decimal. But inside a tightly packed load of lettuce, the reality is very different. A quiet vulnerability hidden between crates, where rot begins long before arrival. The core of the shipment, shielded from direct airflow, becomes a thermal pocket. A few degrees warmer, a few milligrams more moisture, just enough to shift the internal climate of the plant and activate decay from the inside out. Even in containers marked with stable temperatures, engineers have documented an invisible collapse. In tests using thermal mapping, the inner crates, often those closest to the geometric center of the load, reached dew point faster than any others. Air failed to circulate through their layers. The outer crates were cooled efficiently, but the core silently crossed into the danger zone. The data showed a chilling truth. Refrigeration without circulation is not preservation. It's insulation of failure. To break this cycle, packaging became a tool of airflow engineering. Lettuce cartons were redesigned with micro-perforated walls, a technology inspired by tunnel ventilation in poultry housing. These subtle openings are not random. They're mathematically positioned to generate small vortexes as air moves across the load. These vortexes spiral gently between the lettuce heads, forming a layer of moving air even in the deepest recesses of the pallet. What results is a system of airflow layering, not a single blast, but a distributed glide. The impact of this redesign was measured. In comparative studies, shipments using traditional seal crates showed up to 22% more internal rot than those packed with airflow-modified designs, even under identical ambient conditions. Same cargo, same route, same temperature. The difference was in the micromechanics of the packaging, a structural redesign that changed the airflow pattern without changing the container or its cooling unit. These improvements were not theoretical. In the United States, one export company subjected its entire pallet system to wind tunnel simulation. Using infrared thermography, they visualized the airflow within each crate and between each layer. What they discovered was a hidden turbulence, unpredictable microcurrents that pooled in certain zones and bypassed others entirely. After redesigning crate arrangements based on these airflow signatures, the company reported a 31% reduction in spoilage on its long-haul exports. It's not just cooling, it's mapping invisible flows, as if building a miniature climate system within every container. And the logic is simple: simulate airflow inside a pallet the same way one would model heat curves inside a solar greenhouse. Not by container volume, but layer by layer, crate by crate, flow by flow. It's this precision, often invisible to the untrained eye, that separates a crisp delivery from a load of leaf decay. In modern cold logistics, control is no longer about temperature alone. It's about direction, velocity, and internal climate. Each crate becomes its own environment, each layer a terrain of risks and opportunities. And when the air inside the box is finally understood as a flowing architecture, not just a background condition, lettuce stops being a passive passenger. It becomes an active system, engineered for survival. Temperature isn't the only variable in the cold chain. Moisture moves in silence, and in lettuce it remembers. During long-haul transport, water evaporates from the plant tissues, only to be reabsorbed hours later in the sealed environment of the container. This cycle of loss and reuptake may seem harmless, but it triggers a biochemical sequence that has costly consequences. As moisture re-enters the cell walls, the delicate equilibrium is disrupted. Oxygen tension drops, anaerobic zones form, and the leaf begins to ferment itself from within. This is what scientists call moisture memory, a phenomenon where living tissues resume metabolic activity due to rehydration without reactivation of defense enzymes. In the cold, it becomes even more treacherous. The plant appears stable, chilled, preserved. But inside, the reabsorbed water reactivates mildew precursors, subtle microbial threats that gain ground before any visual symptom emerges. By the time the crates reach their destination, shelf life has already shortened. The leaf has already begun to decline. To solve this, engineers turned to a counterintuitive solution: remove moisture without drying. Floor trays using desiccant materials with variable saturation thresholds were developed, not to dehydrate the cargo, but to balance the ambient relative humidity within an extremely narrow window. These trays absorb only passive humidity, and only when the air crosses a defined saturation point. In doing so, they reduce condensation on the crate's inner walls, prevent rehydration of the leaf, and slow down the invisible metabolic switch that turns freshness into decay. The results, when measured, told a story of subtle engineering making a profound difference. Containers equipped with variable desiccant cycling retained Grade A visual quality for up to 72 hours longer than those using fixed-point refrigeration alone. Not because they were colder, but because they maintained atmospheric equilibrium, the unspoken balance between evaporation, absorption, and structural silence. In the Netherlands, a logistics firm applied a similar principle with crate-level innovations. Under each layer, they inserted dual-phase moisture separators, materials capable of alternating between absorption and vapor buffer depending on ambient conditions. After a single season, return rates from European retailers dropped by 18%, attributed not to faster delivery or lower temperatures, but to internal climate stabilization. Lettuce arrived visibly unchanged, but biologically, it had traveled through less stress. The cold chain, at this level, is no longer mechanical. It is biomechanical. It treats each leaf not as a product, but as a structure under tension, absorbing and releasing water in microscopic exchanges. The breakthrough is not in what we remove, but in understanding what the plant retains. Track the retained humidity, map it per layer, predict where the air will turn back into liquid, and stop it before it condenses inside the tissue. This is not about more power or colder air. It is about design, the choreography of air, water, and time. In a sealed container with no room for error, lettuce becomes a test of our ability to control what we cannot see. Moisture moves silently, but the systems that control it must be anything but passive. They must anticipate, respond, and regulate, like a living architecture designed to protect another. Before we move on, take a moment to check the pinned comment below. If the engineering behind cooling a leaf like this fascinates you, what we've prepared there might surprise you even more. It's made for those who understand that real innovation happens in the details. In agriculture, precision starts in the soil, but it doesn't end at harvest. Just as planters adjust their force to root resistance based on moisture sensors, cold chain systems must adapt to the biological fragility of what they carry. Lettuce, with its thin cellular walls and high water content, doesn't tolerate average conditions. It requires a system that reacts to its inner state, not just the ambient air. This is where logistics merges with field biomechanics. In the Emirates, one cargo operator uses STEM-embedded sensors to monitor core temperature in real time. Data from each crate controls localized airflow. The cooling system isn't set. It listens, adjusts, responds. This marks a shift. Refrigeration becomes biological intervention, not static preservation. Instead of freezing or slowing, the goal is to pause metabolism at its edge, to hold each leaf in balance, just before enzymatic activity begins to break it down. Every second becomes deliberate, every degree calculated. What emerges is a logistics system modeled less like a machine and more like a living environment. So the question remains, if we regulate seed depth by the millimeter and water by root zone profile, why are we still cooling lettuce by tonnage? Why treat a living tissue as if it were steel? The answer isn't just technical, it's systemic. Because the cold chain is no longer a container, it's a continuation of the field, a silent, engineered extension of life in motion, designed not just to transport, but to protect what feeds the world. And before you go, check the pinned comment. It's something you probably didn't expect, but might be exactly what you're looking for.